For this problem, we're given with oranges, grapefruit, and tangerines. The heat transfer coefficient for velocities between 0.11 and 0.33 meter per second is determined experimentally. So this equation here is where we can get the value of heat transfer coefficient based on the thermal conductivity of air, the Reynolds number, and then the characteristics length, which is the diameter of the orange. Oranges are cooled by refrigerated air. So the fluid involved here is air, which is at 5 degrees Celsius and 1 atm with a velocity of 0.5 meter per second. So we have to determine the initial rate of heat transfer from a 0.7 diameter orange initially at 15 degrees Celsius, and the thermal conductivity of orange is 0.5 watt per meter degree Celsius. We also determine the initial temperature gradient, so that's delta T over delta Y or delta R, and then we have the average, the value of the Nusselt number. So based on this given. So to find the initial rate of heat transfer, so first is we need to clarify our assumptions. Assumptions are important again because they will simplify your solutions. It is you that will identify your assumptions based on your understanding of the problem. The more you solve problems, the more you will also identify with how to create assumptions. So these are our assumptions. Steady operating conditions, meaning there's no change of properties with time. The orange is spherical in shape. Convection heat transfer coefficient is constant. We need this assumption for us to use the formula without necessarily adding up. So we just use one single convection heat transfer coefficient over the entire surface. Properties of water is used for the orange. So we also take note that the fluid that we will use here to get the properties for the orange, we use the properties of water. So properties. So the properties that we will use in solving these problems are first your thermal conductivity K, which is given. That's the thermal conductivity of the orange is 0.5 watt per meter degree Celsius. However, to get the thermal conductivity and kinematic viscosity of air, we need to solve first the film temperature. Again, the film temperature is just the average of the temperature of the fluid and the temperature of the surface. So that's 15 plus 5 over 2, so that's 10 degrees Celsius. So it is at 10 degrees Celsius where we should get the value of K air as well as the kinematic viscosity. So looking at table A15 at 10 degrees Celsius. So at 10 degrees Celsius, the value of K, thermal conductivity, is 0.02439, and the kinematic viscosity, V, is 1.46 times 10 to negative 5. Take note that you can also derive from this table the PR, Prandtl number, dynamic viscosity, Cp, and density, should this be necessary in our solution. For this one, we will just use K and kinematic viscosity. So the initial rate of heat transfer from Newton's law of cooling, so that's very familiar to us, I think, already. So that's H Ts minus T infinity times the surface area. So we don't have the value of H or the coefficient, convection coefficient, but it is given in terms of the Reynolds number as well as the diameter and the K of air. That's why we need to get the K of air initially. So from the given, H is in terms of the function 5.05 K air R e to the power of 1/3 over D. So first, because K is already given, so we don't solve that anymore. D is the diameter of the potato. That's also given. That's 0.07 meter. And then the Reynolds number. So our general formula for finding the Reynolds number is VD over V. So it depends on the characteristics length. So some equations would use Vx over V. So as long as you understand what X or D means, those are your characteristics length. So those are usually given in the problem. So the characteristics length, so this is your x here. So in this case, our characteristics length is d. So that's why we have vd over v. Sometimes it's vl over k. So meaning the characteristics length is l over k. So it depends on the given. So for this problem, our characteristics length is d. That's why we have velocity is 0.5 meter per second. It's given. Then 0.07 meter, that's the diameter of the orange. V here is our kinematic viscosity. So we find that in the table. That's why we look at it initially in the table, and that is 1.426 times 10 to negative 5 meters squared per second. Solving for that, so our Reynolds number is 2,454.417. If you're going to evaluate this Reynolds, this means that the air is in laminar. So laminar siya because it's less than the critical Reynolds number, which is 5 times 10 to the power of 5. So solving for h, substituting all the values in this equation here, so we can get the value of h, so that is 23.735 watt per meter squared Kelvin. And then finally, we can use we can plug in all our data in this equation. So that's we have Q convection is 3.65 watts. So take note that for the surface area of the potato, we just use pi diameter squared. So the frontal area of the potato is, or the surface area of the potato, so the entire surface is pi d squared. That's why we have pi 0.07 meter squared as our surface area of the potato. So that's our initial rate of heat transfer, 3.65 watts. The next question is to find the value of the initial temperature gradient inside the orange at the surface. So for the initial temperature gradient, so we will use the same formula that we use for problem number 1. So substituting the value of h, that is, so why is it that so for this one, so our h is the h of the orange. So we derive that in finding here, that's 23.735. That's why we have 23.735 here, and then ts minus t infinity, so that's already given, over the k of the orange, because what we wanted to find is the initial temperature gradient of the orange. That's why we use k of the orange and not the k of the air. So do not be confused. We use k of the orange here instead of using k of the air because we're looking for the initial temperature gradient in the orange. So that's why we have negative 474.7 degrees Celsius per meter. So meaning there is a difference of 474.7 degrees Celsius per meter of the radius of the orange. So the last one that we need to find is the Nusselt number. So the Nusselt number, so if you're familiar, that's h times the characteristics length over k. For this problem, our characteristics length is d. So that's why we have hd over the k of air. So instead of using L, the characteristics length is d, and it's given. So substituting all the values, so we have 68.12. So that's our Nusselt number. So the Nusselt number is based on the property of air, again, and not on the property of the orange. Thus, we use K for air and not K for the orange because we are evaluating whether the air is turbulent or laminar. So that's how you solve sample problem number 2.